All right, anyway, so circular motion. You know what that means? You're moving around in a circle. Specifically, we're going to talk about things moving at a constant speed. So maybe 50 miles an hour around in a circle. But things that are moving at a constant speed around in a circle are considered to be accelerating. Why is that? Well, even though the speed's constant, technically velocity is a combination of speed and direction, magnitude and direction. So if the direction is changing, there must be an acceleration present. And you can think back to Newton's laws. Object in motion will stay in motion, object at rest will stay at rest. That's a natural tendency for objects, unless there's a what to change it? A force. And from Newton's second law, we know a force equals what times what? Mass times acceleration. So we know force is associated with acceleration. So if anything is changing direction, it must be because of a force anyway. And that would, of course, have an acceleration associated with it. Just for the record, what is the force that would allow you to move in a circle if you're driving your car? Connor, you might know. What am I getting at? I know we haven't talked about forces yet, but if you turn your tires, you want to move in a circle, turn your tires doesn't mean diddly squat without what force? Friction. So if you imagine doing that on ice, well, so what? You've turned your tires, but you're going to keep on moving. So friction would be the force that would keep you moving in a circle in that example. All right, so the acceleration that would be present if you're moving in a circle is called centripetal acceleration. Centripetal meaning center seeking, and we'll prove that here in a second. Okay, so here's sort of some necessary information to do this little proof we're going to do on the next slide. Hopefully you remember arc length. If you multiply the angle times the radius, as long as the angle is in radians, you would get the arc length. And also, we'll actually see this a little later in the year too when we do simple harmonic motion. But sine of an angle divided by that angle is roughly about 1 if you're talking about a very, very small angle. So it has to be a small angle for that to be true. Okay, so sort of using that information, I want to find the acceleration for this particle, which is moving in a circle. As it moves from here, from point P to point Q, I want to find the magnitude and direction of the acceleration of that particle. And I know there must be acceleration because it is changing direction. So we're moving from P to Q. We're also assuming the velocity, well, the speed here has the same magnitude as at Q. So even though these directions are definitely different, it's the same speed. Okay, so we're going to solve for acceleration. Oh, and there's our answer. Bit of a giveaway. Hopefully you can fit this in your blank slide here. Let's see if I can fit it on here. Yeah, okay, so here's just sort of our given information. Let's see if I can use my picture just for a moment. All right, well, I'm asking you to find the acceleration. Okay, so what's really one of our most basic acceleration formulas? Okay, change in velocity over time. Perhaps not in white. Is acceleration a vector? Yes. It has a direction and a magnitude. Okay, so this is a vector equation. So we have to be really careful, and this is a really important part about physics. When things are vectors, you can't just go like willy-nilly throwing things into our equations. You've got to make sure directions match. So I can use this equation that's any direction, but I have to be consistent. I can't just throw in, this value and this value in this equation because these are clearly different directions. What I can do, like projectile motion, is analyze my directions separately. I can analyze, x information separately from y information. So really, if I want to know the magnitude and direction of acceleration, I need to solve for it twice. Once as an x component and once as a y component. Okay, so I know I need these formulas. Let's start with the x direction. That'll be a little quicker for us. I want to do change in my x velocity over time. Well, what is my x? Yeah, they're the same, right? Even though this one's VQ, if the magnitude was originally the same, and you can even solve it. We did have the assumption that this velocity is the same as this velocity. So this would be, this component would be v cosine theta. Same here, though, v cosine theta. So in the x direction, final minus initial is 0, like you said. Okay, so x direction is already done, which is kind of nice. So now I know the answer to my acceleration is only going to have a y component. Well, all right, so let's look at our y info. What would we call, and again, this is sort of like some of the short answer problems you see where you want to use the given variables. What is this initial y velocity related to v and theta? Yeah, so this is equal to v sine theta. How about over here, though? Negative. Yeah, this is going to be going down. So while the magnitude would still be v sine theta, that velocity has a different direction. So we need to indicate that with our negative sign. Okay. You don't need to rewrite this. You gotta have it on your picture. So final was negative, minus initial was positive. Okay, so we're sort of stuck with this. How in the world does that turn into the answer you guys have down here? We have no idea. All right, well, one issue was that time was not given to us. So we've got to actually substitute out for time. So what's another expression we maybe know about time? And not velocity, but speed. What's a very simple speed equation? Distance over time. Not velocity is displacement over time, but for speed, which I won't put the vector hat on there, is, distance over time. The speed isn't changing. Okay? Velocity is, speed isn't. So my speed, which was simply v, equals distance over time. But what was the distance traveled from P to Q? So think back to the slide you just wrote before this one. That was kind of the... Yeah, it's the arc length formula. So if I wanted to know this distance, I'd want to talk about the arc length. But very good. Based off of the information we're given, if we're given theta, the full angle to get that arc length is 2 theta. Okay, so that's my distance traveled. And just swap the t and the v. Yeah, and then that's going to go over here. How are you guys doing fitting that in that little slide? Good? Okay, so again, the original goal is to get acceleration. We know that the x component was 0. We're trying to find the y component of acceleration. We just did change in velocity over time, but we needed an expression for time because time was not given. So we did our very basic speed is distance over time equation, the distance being the arc length, and now we're going to plug that in and try to simplify a little bit. So of course up here we got -2 .
Why did you come up with square?
Yeah, that one gets kind of pulled all the way up there. And you do end up with that sine of theta over theta. And what, according to the slide before, does that equal for a small angle? 1. So that's going to go away so long as we assume our angle is small, which we would be doing if we're trying to find that like instantaneous velocity between points, assuming they're very close together. And of course we have a set speed. What does a negative sign mean here though? Yeah, it's y, so it's going down. Okay, so all that relates back to my picture means, you know, the average acceleration between these 2 points will be straight down. Of course, the average between these 2 points would be right smack in the middle anyway. V squared over r. So for circular motion, your acceleration is given by v squared over r. The direction is going to be center seeking. For our example, we had that negative sign, so that meant down, but it's always going to be center seeking direction.
So it could be to the left or up.
Yeah, so of course, yeah, if it was over here, you know, what would be the direction of acceleration if I'm talking about the particle right here, if I could ever draw it? Which way? Left. And in unit vector notation, what would that be? What?
Would it still be negative?
Negative what letter? Negative I. Good. And those are kind of common questions too, just simply like which way is the acceleration going, you know, if I'm here, or if I'm here, or if I'm here. You know your unit vector notation. Just know it means center seeking. Okay. So that was all a long proof, simply to prove this formula for acceleration of something moving in a circle. Two other circular formulas that are just helpful. This is sort of essentially distance over time. Capital T in science means period. We'll see that in later units as well. Period is just the time of a cycle, or in this case, the time of one circle. And our circumference is 2 pi r. So that's sort of our, distance over time. Or you could swap them, either way. But those are good circular formulas to know. All right, if you just go to your book real quick, let's do this one, page 66. Which I think is the last checkpoint. Lucky winner. It's hard to shuffle like 10 cards. Oh, it's Emily. Okay. Come on. Okay, so page 66, number 6. An object moves in a circular path in the xy plane with the center at the origin. When the object is at x equals negative 2 meters, its velocity is negative 4 meters per second, j. So let's just set that up for a second. Okay, so we have a circle. It's either moving this way, maybe it's moving this way, not really sure. And it said specifically when x is negative 2. So right here, the object has a velocity of negative 4 meters per second, j. So which way is that? Down. All right, give the objects a velocity and then b centripetal acceleration at y equals 2. So what would be the velocity at y equals 2? 4 meters per second. Keep going though. Which way? It's going that way? You're doing the acceleration. So if this velocity is down, yeah, it must be going this way. Yeah, so the tangent to this path would be negative I. All right, and then your next question was the centripetal acceleration also here. So which way is it going to point? Down. And our formula is v squared over r. So it'd be 8, negative 8, I or j? J. There you go. So that's the acceleration. So if you're given a problem like that, your first task is just kind of figure out which way the particle is moving. Is it moving clockwise or counterclockwise? In this case, given the information we started with, it must have been going like this, counterclockwise. So of course velocity up here would be tangent, which would be negative I. And then acceleration, we used our formula, but we knew it had to be center seeking, so it had to be negative j. Questions on that? Okay. That's sort of it for our intro to circular motion. Oh, except for one example problem. Somebody got a calculator? Needs to be real quick, I promise. Except for the annoying big numbers. Okay, in one model of the hydrogen atom, an electron orbits a proton in a circular radius of 5.28 times 10 to the negative 11 meters with a speed of 2.1 times 10 to the 6 meters per second. All right, so what is the acceleration? It doesn't ever ask us at like one certain point, so we just know we know it's going to be center seeking. But what's the formula for acceleration? V squared over r. Done. Plug it in. Be careful with your...
9 to the 22nd.
Let me write it down. Okay, 9 to the point anything?
9.00075.
Units?
I guess that has to be units? Meters.
Per?
Second space.
Yeah, everything's in SI units here. Anyone else get that? Okay. Be careful with your graphing calculators. I always see errors when we're trying to do the 10 to those.
I did the E.
Make sure you're squaring what you think you're squaring. When in doubt, use a bunch of parentheses. You know, make sure that 10 to the negative 11 stays in the denominator. Okay, that was easy. B. What is the period of motion? Okay, that's the formula from the page before. Period again is capital P. What's the formula?
Oh, 2 pi radius and
Good. Pretty much circumference over speed. So oh, I wrote that backwards. What's
1.52 times 10 to the negative 16.
okay? And what unit would that be for period?
Times what is that?
Yeah, this is a time, so that's seconds. So that's the time of one revolution, of one cycle. Okay, know your formulas? That would be a piece of cake.
Are those formulas on the equation quiz?
Yes, this is still part of Unit 2. And there's actually 2 more. They're sort of the same, but... All right, questions, comments, concerns on circular motion? Great. Last little topic in Chapter 4 is relative motion. Okay, so we were talking about reference frame. Almost always we just are comparing something to the ground, stationary ground. We're talking about the ball is moving at 20 meters per second, you know, relative to what? Almost always it means stationary ground, but it doesn't have to. And if we keep up with what objects we're talking about, it can make relative motion problems a lot easier. But here's just a little scenario. Bart is still. This car is moving. He can see this car, but perhaps he can't see the Jeep. So maybe we know information about the car relative to Bart, and maybe the car knows what the Jeep is doing. So we have information about the Jeep relative to the car. So we'll use those letters, B for Bart, C for car, J for Jeep. And if it's a second letter, it means relative to that thing. So here is one basic equation. I'll give you the more generic version of it in a second. This is simply talking about position. And this should make sense. If Bart wants to know the position of the Jeep, but he can't see the Jeep, he can only see the car. If he knows the position of the car and the car knows the position of the Jeep, we can just add all that up and know the position of the Jeep. Does that make sense? So the way this is read, well, the position of the Jeep with respect to Bart would be equal to the position of the car with respect to Bart plus the position of the Jeep with respect to the car. But hopefully that little drawing makes sense. If you just added up those distances, it would be the same total distance. Okay, now the same is true for velocity. So maybe we want to, Bart wants to know how fast the Jeep is going, but again, Bart can't see the Jeep. Jeep's far away. For whatever reason, he can't figure that out. But he does know how fast this car is going, and this car does know how fast this Jeep is going. Then we could figure out the speed relative to Bart. Same formula. just a v instead. All right, reference frames that move at constant velocity are called inertial reference frames. And the interesting thing here would be, regardless of what inertial reference frame we're in, we should always measure the properties of physics to be the same, and also the accelerations we measured to be the same as well. So that's somewhat of a shortcut in your problems. If you know the acceleration in one inertial reference frame, it's the same in the other. Quick example. This is not talking about the velocities. The velocities could be very different, but if they're constant, they would still measure the same acceleration. Like, let's say we're talking about that again. Relative to BART, maybe that Jeep's going really fast. Maybe it's going, I don't know, 30, that's a good 3, 30 meters per second, but it was originally going 26 meters per second. And he watched this happen for 2 seconds. So what's the acceleration that BART observes? Okay, so that's from BART. Now, the car is moving behind the Jeep. The car is moving too. So is the car going to think that the Jeep is going as fast? No, but the car is still going to see the same rate of change. Maybe relative to the car, that Jeep's only going 10 meters per second. Faster than it. So it sees a change of 6 to 10 in 2 seconds. Different speeds, but it's still going to give you the same rate of acceleration. Does that make sense? Okay. And the other thing I was saying about inertial reference frames, if you're moving at a constant velocity, you measure physics the same. So it doesn't matter if you're doing experiments while you're still or while you're moving at, 50 miles an hour. Which leads into another classic physics problem. Zach's looking a little tired over there. So I kidnap him, blindfold him, put him on a high-moving train, really smooth too. It's like magnetic kind of levitation trains, amazing, super fast. I black out all the windows. Zach wakes back up. And he slept through any acceleration periods, because you definitely can feel acceleration. What can Zach do to decide if he's moving or still? Nothing. If you slept through the acceleration period, there are no experiments you can do to figure out if you are moving or still. We'll have one of the checkpoints in a second here that asks about just like tossing a ball up and catching it in your hand. Well, what if you just try to do that? Okay, you're in this train, nothing's around except for apparently this ball. It's pitch black, but you've got good night vision. If you're moving, shouldn't the ball maybe not fall back in your hand if you toss it up? Shouldn't you move out from underneath it?
You're kind of throwing it like at us.
Yeah. You have a horizontal velocity, you're automatically giving that horizontal velocity to the ball. So, you catch it in the same spot. And all the air in the train will be moving along with it as well. Okay.
Well, I guess that would be considered acceleration.
What?
Going around like a turn or something.
Yeah, now see, that would be exactly, you would know that. You can definitely feel in a vehicle if you're in a turn, but that's acceleration. You can feel acceleration. So, objects in different inertial reference frames, again, meaning there's a constant velocity there. We'll measure the same acceleration. Of course, true for 2 dimensions as well. Just make sure you're analyzing x and y separately. Okay, so these are the equations I would like you to know You can think about Bart and the car and the Jeep, but this is just sort of the generic formula. I always like to think about it as you take the two letters, the P and the A. So this is like the position of P with respect to A, and like split them up. And then stick some other object in there. So and then if you're doing a relative motion problem and you can like keep records or like read the problem well and know what's with respect to what, if you write down your letters correctly, sometimes even if you are confused about what the problem is saying, you can just plug in the numbers where they should go based off of the letters, knowing that the letters should be spread apart with a new letter in the middle. So position of P with respect to A equals the position of P with respect to B plus the position of B with respect to A. Okay. So we've got two problems, and then I want to just finish up the discussion questions. All right, now this one's somewhat simple. I know you could probably do it in your head, but I want to drag you through the notation because maybe it'll help for a later. But you might need a little room off to the side. I guess you got room maybe at the bottom. You can fit these two. Okay, so a boat is traveling upstream at 14 kilometers per hour. Let's just pretend that this says hour. I don't want to do any unit changes. But anyway. A boat is traveling upstream at 14 kilometers per hour with respect to the water of a river. The water itself is flowing at 9 kilometers per hour with respect to the ground. What's the velocity of the boat with respect to the ground?
What does this mean? Like the river is moving downstream?
The river's flowing in the same direction.
Yeah, is it flowing in the same direction, or is it going up against the current?
We would always say a current's downstream, a river's flowing downstream. Okay, so let me draw my river. Here's my boat. Okay. And the boat's going upstream, the river, of course, going downstream. So we've got to keep track of the respects to. So what's the velocity of the boat with respect to the ground? Okay. Velocity of boat with respect to ground. That's my question. Okay. What do I know? I know this 14. So a boat is traveling upstream at 14 kilometers per hour with respect to the water. So I'm going to write boat with respect to water.
Anything like relativity, like if you're sitting on a train and two trains are going the opposite way?
Yes, and I'll comment that we're not talking about like super fast speeds, because I'll cut this other classic problem for one moment. Classic question is in relativity, all right, well, if nothing can go faster than the speed of light, what if we have this huge rocket ship? That is not a wing. Which, I don't know, do we even need wings in space?
Probably not.
Kind of spoiler.
Okay. Huge vehicle of transportation in space.
It looks like a duck.
Inside, we launch mini rocket ship. If this rocket ship's going at 0.75 times the speed of light, and the mini rocket ship inside gets launched at 0.75 times the speed of light relative to the big ship, could we not just say it's going faster than the speed of light relative to somebody outside? No. So those equations only work at slow speeds relative to the speed of light. There actually are other equations you have to use once you approach the speed of light, which does mean technically those are wrong, but they're approximately true at our slow speeds. The limits approach that at our slow speeds. But that's for a later date. Good question, though.
So this is like the longer approaches zero, technically.
Yeah, well, as the limit approaches, yeah, something much smaller than c.
Wait, are we actually go over into?
Perhaps. It's not part of our AP unit, but I do have a lovely little lesson on it.
Sounds like a big one.
What?
Sounds like a big one.
Yeah, it is mind-blowing, frankly.
I saw this thing, it was about Usain Bolt running the 100-meter dash, and he went fast enough to where, like, from his point of view, the track shrank by like 5 nanometers.
Yes.
So he didn't technically run the 100-meter dash.
Yes. At fast speeds, again, relative to the speed of light, things shrink. They become more massive. So as you move faster, you become heavier, shorter along the direction you are moving. So if I was going sideways, it would shrink this way, and time moves slower. So that's one of the big misconceptions of our physical world, is that time is a constant set thing. No, time is relative to how fast you're moving. Good questions. Later. Arguably more fascinating than our boat in the river. I'll grant you that. But I'm going to finish with the river problem. Okay, the water itself is flowing at 9 kilometers per hour with respect to the ground. And I do need to start worrying about directions. Yeah, if this is moving, downstream, the way I've drawn my little picture, this should be negative. All kilometers per hour. So you can kind of just, I've kept good records. I've got all my letters correct. If I can remember that equation where this should be like separated and the different point of view in the middle, so the water's in the middle, this is already sort of set up. And this is in one dimension, so this is fine. This is our vector equation. The velocity of the boat with respect to the ground should equal the velocity of the boat with respect to the water plus the velocity of the water with respect to the ground. So our answer should just be 5, which you probably could have figured out a long time ago. All right. What was the other part of that? If the boat runs aground, so that it takes 2.5, okay, that doesn't make sense, but 2.5 hours to come to rest relative to the shore, so relative to the ground, what was the acceleration of the boat relative to the ground? So what is the velocity of the boat relative to the ground initially? Velocity of the boat relative to the ground initially. 5. That's what we just found. The final velocity of the boat relative to the ground, if it just runs ashore, is what? 0. So it's asking for acceleration. That's our final minus initial. But it's got to be relative to the same thing. I can't just pick different boat velocities relative to different things and plug them in. So these are both relative to the ground. So we get 5. Sorry, not 5. It's 0 minus 5. Over the time of 2.5, assuming my units were the same, but they're not. It's negative 2. Because it stops. It runs aground. Gets stuck in the shore.
That's a slow boat.
Yeah, I meant for it to be 2.5 seconds. But then I didn't obviously change the rest of it. Okay, so that's part B. On part C, what's the acceleration of the boat relative to the water?
Still negative.
Ah, if we're smart enough and we know that,
Acceleration should
yeah, and we know that the acceleration, regardless of reference frame, should be the same, we should know the answer is going to be -2. Should be the same. So we can either stop there or we can prove it to ourselves with boat relative to water info. So let me use the same setup. If I want velocity of the boat relative to the water, final. What's all this other final stuff? What's the velocity of the boat relative to the ground?
finally.
Finally, sorry, 0. I'm sorry, this is now final. What was the velocity of the water relative to the ground, or did that even change? Doesn't change, so that's just what? -9. So the velocity of the boat relative to the water would be 9. Like the water thinks it's still and the boat's moving at 9, although it's vice versa. So to do the same acceleration equation, but with a different reference frame with everything relative to the water, the final is 9. What was the initial velocity of the boat relative to the water? 14. Still over 2. Be the same answer, 5/2.
2.5.
2.5 is negative.
Divided by 2.5.
Divided by 2.5. Thank you. But again, cut to the chase. You know, if you have multiple choice questions like that, and it's asking you for acceleration over and over and over again, once you've got it right the first time, that should be all the rest of the answers. Okay. Now this is, again, a vector equation here, but we were only dealing with one dimension anyway, so we didn't need to worry about components or anything like that. But now let's do an example in 2 dimensions. Last one. We still got a couple discussion questions to do. Okay, you might be able to fit this one here. In rugby, a player can legally pass the ball to a teammate so long as the pass is not forward. Suppose a player runs parallel to the field's length. Let me draw out my field. Okay, so here's my field. With a speed of 4 meters per second. So how should I keep up with that as a variable? Velocity of what with respect to what? Good. Velocity of player with respect to ground. That is how I do it. But it is a vector, so we got to pay attention to our drawing. While he passes the ball with a speed of 6 meters per second relative to himself. So how would you label that?
And the ball according to player.
Good. Velocity of ball relative to player. What is the smallest angle from the forward direction that keeps the pass legal? So to keep the pass legal, we want to know the velocity of the ball with respect to the ground. It doesn't even ask really for the magnitude, it just asks for the direction. So the velocity of the ball with respect to the ground And look, here's my B and my G. So it's like saying this is equal to, these two velocities added up. But they are vectors, so we've got to be careful. If I just draw on the 6 in the same direction like this, well, does that fit my requirement here? We got to pass it so the pass is not forward. So pass cannot be, if this is where my player is, pass has to be like this as a net velocity. So can the rugby player throw it forward at all? No. If he's running forward, he's got to compensate for that by throwing it backwards. Now he can still throw it to the side, but here's my player with respect to ground. I'm going to add on ball with respect to player. Again, it's a vector, but I'm going to add it head to tail. So, and make sure you label these in your drawings. Maybe this will make a little more sense. This is the velocity of player with respect to ground. I'm adding that to velocity of ball with respect to player, which is 6. I don't exactly know this angle yet, but I know it's going to be 6. And I know this. And my net has to be perpendicular. It can't be forward at all from where this player is. Does that make sense? So this little dashed line is really the resultant. And again, I don't actually care what the magnitude is. So I've got a triangle with 4 and 6, but I do know it would be a right angle if it's perpendicular. And it asks me for the angle from the forward direction. This is how I would read that. So here's the forward direction. From the forward direction, what is this pass angle? Or probably that would be acceptable.
So we should find the one on the inside.
Yeah, so find that one and subtract from 180.
But what do you have to find?
This is a problem from the book, and they give you the bigger angle.
You don't really need to find velocity.
Yeah, you don't need to do Pythagorean theorem. It doesn't ask that. It just asks for the angle.
So just do it like the inverse.
Yeah, well, what trig function? Looking at a triangle, if this is the right angle, we know the hypotenuse and the adjacent. It's got to be a good inverse cosine.
That'd be 131.
Oh. Thank you. So that's the inside angle, but that's going to be what?
The inside angle is 48.2. 0.19.
Okay. But actually the angle they're looking for is...
Yeah,
31.8? Okay, so that adds up to 180. But this was the answer in the book. That's the angle from the forward direction. From there. Ta-da.